Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going over our final topic, divergence theorem. I say final topic because this is the final topic that I'll be teaching in Calculus 3. Don't worry, I'll be back for sure teaching another math class, tutoring I guess you could say, but this is going to be the last video in our Calculus 3 series. So I guess going into what divergence theorem is, it essentially relates surface integrals, in other words, flux integrals, to triple integrals. And I specify the flux integrals part because, well, what we're doing is we're actually going to be relating it to vector surface integrals. And just recall that vector surface integrals typically are going to calculate flux. So unfortunately, the bad news about divergence theorem is it's kind of difficult to draw a depiction of or even create a metaphor for. So therefore, I'm not going to be doing that today. But I can explain why the divergence theorem is used. So as for it is in most Calculus 3 applications, it's going to be able to simplify calculations quite a bit. And this is actually kind of flippable here. And I guess I can't really say this yet for the divergence theorem, but just like we talked about last video with Stokes' theorem, it actually could make a surface integral easier by transforming it into some other integral, or it could make that other integral easier by transforming it into a surface integral. And then another key topic it's kind of in is electromagnetism. That's kind of one of the bigger applications of the divergence theorem within physics. So I guess without further ado, let's just go ahead and get into what the divergence theorem is. Well, the divergence theorem states that for a solid region V in 3 dimensions bounded by a closed surface S, then the double vector surface integral is equal to the triple integral of the divergence of F over V. So a couple things I want to break down here. For a solid region V in 3D bounded by a closed surface, the reason I highlight that kind of closed part is because that is how we're going to be using the divergence theorem. I know for a while it was actually kind of unclear to me when I was able to use the divergence theorem and why I wasn't able to use the divergence theorem every single time I had a surface integral. And well, the answer is it's going to be closed. So meaning what? Well, typically when we're having surface integrals, well, we're having shells of something. So for example, a cone, right? Well, we're just going to have the cone aspect. We're not actually going to have a lid on the cone, right? So that's kind of what that is. Well, the divergence theorem works is if, well, we had a plane cutting off that cone. That's kind of when the divergence theorem works. Another part I kind of want to talk about here is the divergence of F. I guess recall that the divergence represents the kind of source or quote-unquote sink strength at any point inside of the volume in this application here. What I mean here is, well, the divergence, if it is greater than 0, well, then it's going to be incoming, right? That means in kind of like a fluid sense, if the divergence is greater than 0, then we're actually going to be getting fluid inside of our 3D region. And if it is less than 0, then it is going to be a sink, so to speak, wherein it is actually going to be dumping out fluid. What else to say about this? I guess the fact that it's a triple integral, meaning it's going to sum up all of the divergence inside of the entire volume. Surface integral, we know that it calculates the total flux or the total net flow exiting some kind of boundary S. I guess that's all we have to say about divergence theorem, so let's just go ahead and get into an example. We're asked to find the flux of our vector field y, x, z through S, which is the boundary of the solid V enclosed by z is equal to 1 minus x squared minus y squared, and the plane z is equal to 0. So I already drew this out for us here. Like I said prior, it could be a little bit difficult for us to understand when we're using surface integrals versus when we can apply the divergence theorem. Well, this is kind of a good example here. We have some kind of upside down paraboloid, right? This is kind of our upside down bowl shape depicted by the top here. Well, if that was all that it was bounded by, and let's just say our z was bounded by, well, for this instance, we'll say it's bounded for between 0 and 1. What that means is that, well, it's actually open at that bottom point z, wherein when we have a plane here, z is equal to 0, that means that this is actually going to be closed. So meaning that we actually just kind of have a bowl with like a lid on right now, whereas if we didn't have that plane z is equal to 0, then it would just be a bowl, open lid. So that's kind of how we know when to use the divergence theorem. And like I said, divergence theorem is going to be when it's closed. I can't emphasize that enough. So I guess, spoiler alert, we're going to be using the divergence theorem to find the flux here. We could use the surface integral. So I guess, conventionally, how we find the flux would be this vector surface integral here over some region S. But, using our divergence theorem here, we know that that flux integral there is actually going to be equal to a triple integral of the divergence of our vector field. So we can actually just go ahead and rewrite this as a triple integral. When we take the divergence of our f, dv over some region v. Okay, so without further ado, I guess let's go ahead and get into how to actually solve this. Well, I want us to note that, well, we know how to solve triple integrals here. This is an upside down kind of bowl here that should realistically be screaming cylindrical for us. Why that is, well, from our z is equal to 0 axis all the way up, well, that kind of function there is going to be that z is equal to 1 minus x squared minus y squared. And I guess kind of spoiling the math here, well, this can just be rewritten as z is equal to 1 minus x squared plus y squared. And recall that x squared plus y squared is equal to r squared. So this can just be written as z is equal to 1 minus r squared. So kind of jumping a step almost here, or perhaps all we are doing it intuitively and just kind of think in our head, well, since we are using the divergence theorem, are we going to be using Cartesian, or are we going to be using some kind of other coordinate system here? And like I said, we will be using cylindrical here. But I guess I might be getting ahead of myself here, so let's just go ahead and do our step. Well, what do we want to find first? Procedurally, when we're doing divergence theorem, we're going to want to find the divergence of our vector field first. So I guess that could be argued as step 1. And recall that divergence f, divergence dot product, meaning we're actually going to be taking the dot product of our gradient and our vector field. So we're actually just going to write this all out here. Our gradient, just recall that our I component of our gradient is the partial with respect to x, the j component of our gradient is the partial with respect to y, and the k component of our gradient is equal to the partial derivative with respect to z. And we're dotting this with our vector field. Well, our vector field is given to us as y, x, z. And recall that, well, we're actually going to get a scalar output here. So once again, perhaps it's not so difficult to understand why this may be easier than actually doing a whole surface integral. Obviously, it's not always going to be easy as just having a constant, but sometimes it'll definitely be that way. So we're going to be taking the dot product, which is just going to be the partial of y with respect to x plus the partial of x with respect to y and the partial of z with respect to z. Let's go down the line here. Well, the partial of y with respect to x, that y is treated as a constant, therefore that's going to be 0. Similarly, the partial of x with respect to y is going to be 0. That's treated as a constant, and the only one that actually works here is going to be the partial of z with respect to z. That's just going to equal 1. So our divergence here of our vector field is actually going to equal 1. So pretty simple here. Let's just go ahead and kind of figure out our bounds on our triple integral now. Like I kind of said earlier, I spoiled it perhaps a little bit, that our surface or our triple integral is going to be in cylindrical coordinates. So I guess what are we going to start off with? We're going to be starting off with our z-axis here. I definitely argue that's the easiest. Well, we're coming in from the bottom here, that plane at z is equal to 0. Therefore, our bottom bound will be z is equal to 0. And then we're coming up and exiting through this kind of function there that is represented. I solved for that just a little bit earlier. That's z is equal to 1 minus r squared. Therefore, that's gonna be our bound on z. So let's just start off with dz. I guess 1 is going to be our integrand. Dz, dy, dx. I just kind of like that. Notationally, it doesn't really matter. Never mind, not dz, dy, dx. Sorry. It's actually going to be 1 r dz. dr, d theta. Now, squishing this down into the xy plane here, well, we're going to have a circle of radius. What is the radius? If we plug in z is equal to 0 into this kind of little equation here, let's just go ahead and find it, actually. We're going to have 0 is equal to 1 minus x squared minus y squared. Just add out that x squared, add out that y squared, and simple algebra here, we deduced that our xy plane circle equation is x squared plus y squared is equal to 1. Or we can convert it into r squared is equal to 1, therefore r is equal to 1. What that kind of means is, well, if our r is 1, we found our r, it goes from 0 to 1. And our theta, well, this is a circle, therefore it goes from 0 to 2 pi. It's a circle. It's not a semicircle, it's a full circle. So that is going to be our integral here. Let's just go ahead and solve it. Should be a pretty simple one. We're going to have the integral from 0 to 2 pi, the integral from 0 to 1, and the integral from 0 to 1 minus r squared of r dz dr d theta. This is going to equal the integral from 0 to 2 pi, the integral from 0 to 1, and then we're going to add an rz on here. Evaluate that z is equal to 0, and z is equal to 1 minus r squared, and then this is going to be dr d theta on the outside there. Evaluating this further, we're going to have the integral from 0 to 2 pi and the integral from 0 to 1. Let's just go ahead and simplify this. If we plug in z is equal to 1 minus r squared, we're going to go ahead and multiply this r out on the outside here. So we're going to have r times 1, which is r, minus r times r squared. That's going to be r cubed. And then we're going to subtract that by when we plug in z is equal to 0, which we know is going to be 0. So there's really no need to add minus 0. And then we're going to have our differential now be dr d theta. Continuing along with solving this, we're going to have the integral from 0 to 2 pi, and let's just solve this integrand here. 1/2 r squared minus 1/4 r to the 4th from 0 to 1 d theta, which is going to equal the integral from 0 to 2 pi of, well, if we plug in 1, we're going to have 1/2 times 1 minus 1/4 times 1. So it's just going to be 1/2 minus 1/4. I guess we can go ahead and convert that 1/2 into fourths. So this is just going to be equal to 2/4 minus 1/4, which is equal to 1/4. And then minus, when we plug in our 0, similarly to the last time, if we plug in 0 here, it's just going to be 0. We're going to have 1/2 times 0 minus 1/4 times 0. So our integrand is just going to be 1/4. Our differential is going to be d theta. Therefore, our answer is going to be 1/4 theta from 0 to 2 pi. Therefore, we are going to have our answer be 2 pi over 4, which is equivalent to pi over 2. Kind of a more simple divergence theorem problem to start off with here. Maybe there's not too many notes here. I guess the main note that I want to make is that we were able to use the divergence theorem because the solid V that we were doing was enclosed. Therefore, it is solid. If we didn't have this plane here, then we actually wouldn't be able to use the divergence theorem. Any more notes here? Just remember that the divergence of f is equal to the dot product between the gradient and f. It's kind of a mnemonic that we can use here is, in the past two theorems that I've actually been explaining, it's been the curl of f in the integrand. So curl cross product divergence dot product is a pretty good mnemonic that we can use there. Anything else that I need to note here? I don't think so. Just once again, go ahead and make sure that the boundary is closed and the solid is closed before we go ahead and try to use the divergence theorem, because otherwise it doesn't apply. Let's just go ahead and get into a harder example. Moving on to our final and harder example here for the divergence theorem, we're asked to calculate the vector surface integral where our vector field is equal to 3x y squared, x e to the z, and z cubed. S is the surface bounded by y squared plus z squared is equal to 1, and planes x is equal to 0, and x is equal to 3. A little note here, this is kind of what our region is going to be looking like. Once again, spoiler alert, well, how would we deduce that we can use the divergence theorem here? Well, we know that the boundary is closed. We know that this kind of shape here is closed because it's bounded by two planes, and there's a function here, meaning it's not actually just like a pipe. It is rather like a soup can, perhaps. You could argue it's like. So our planes are going to be x is equal to 0 here and x is equal to 3. And then it looks like we're going to have like a slightly shifted cylinder. What that means is perhaps this is definitely not even perhaps, this is more than likely not a shape that we are used to here. When we are doing cylinders, we're usually used to it being along the z-axis, meaning it's x squared plus y squared is equal to some value. That's something that we're typically used to here, but unfortunately that is not the case. It's actually opened up in the x direction. So I guess my moral of the story here is don't let this freak you out at all. Once again, spoiler alert, we're going to go ahead and use the divergence theorem here. So we know that by the divergence theorem, that this surface integral here, f dot ds over the region S, that's actually going to equal the triple iterated integral of the divergence of our vector field dv over some region V, or E, I guess, in this scenario. We'll use E. So procedurally, let's just go about doing this. We'll figure out our bounds in just a little bit. Let's go ahead and solve our integrand first. Perhaps, if we're lucky, the divergence will be 0. And then we can actually just kind of skip that step. Let's see here. Divergence of f dot product. So we're going to have the vector, the partial with respect to x, partial with respect to y, partial with respect to z, that is our gradient, dotted with our vector field, 3xy squared, x e to the z, and z cubed. Let's go ahead and solve this. We're going to have our first term be the partial with respect to x of 3xy squared, plus the partial with respect to y of x e to the z, plus the partial with respect to z of z cubed. And of course that is going to equal 3y squared. Taking the partial of that first term, that's going to be the partial of 3xy squared with respect to x. That x is just going to cancel out and turn into 1. Therefore, we're going to be left with a 3y squared. Second term here, we're taking the partial of x e to the z with respect to y. Well, there's no y values in here. That x e to the z is just treated as a constant. Therefore, that is actually going to be 0. And our final term here is the partial of z cubed with respect to z. Simple power rule there, that's just going to be 3z squared. Looks like this is going to be our divergence theorem. Our divergence of f. And just really quickly, maybe I'm spoiling something, but we're just going to factor out that 3 and make it a little bit easier. 3y squared plus z squared. Okay, now moving on to our kind of bounds on our triple integral here. Well, once again, I want to make sure that we know that just because this is in a different plane does not mean that it's any different. It can still be treated procedurally the exact same as something that we are already used to, which is polar. I guess I just kind of want to draw a parallel here. Well, our polar is typically in the x and y region, but we're shifted to the y and z region. I just don't understand why we can't treat it as the exact same, wherein our horizontal axis is going to be our cosine theta, and our vertical axis is going to be our sine of theta. It's essentially no different here compared to if this were in the xy plane. Well, we would be thinking to ourselves, this is an easy integral. I know exactly what the bounds are. I know how to find the bounds. I know how to transform it into cylindrical. Well, what would we do? We would have our x equal to our cosine theta. Recall that is our horizontal axis. And our vertical axis we would turn into our sine of theta. And our z would be the exact same. Our z would be equal to z. And what I mean to say here is just because, like I said, we're switched into a different coordinate system, or not a coordinate system, but a different axis here. It opens up in the x-axis. Why can't we treat the x-axis as the z-axis regularly, the y-axis as the horizontal axis in our typical polar conversion, which is going to be x, and the z-axis is going to be treated as our vertical axis? Maybe I'm overcomplicating this, but I'm pretty much just trying to say that we're going to treat y as our cosine theta in this kind of conversion, and our z is going to be our sine of theta, wherein our x is going to equal some kind of bound. So kind of demonstrating what I'm talking about here, we're going to turn this into cylindrical, and how we're going to do that, it's procedurally the exact same. Let's go right at our integrand here. We're going to pull out that 3, why not? Y squared plus z squared. And then we kind of want to figure out which order we want to go in here. Once again, I kind of spoiled that we're changing to cylindrical here. So what order do we want to go in? Well, typically when we're doing cylindrical in the xy plane, we do r dz dr d theta, wherein our dz is opened up. So that's where our cylinder is opening up. So let's just go ahead and go our dx first. That's going to be treated as where our cylinder is opening up. So our bounds on x are actually given to us. We have the planes x is equal to 0 and x is equal to 3. So that's pretty easy there. Now let's just go ahead and smush this picture into the yz plane here. Once again, that y is going to equal our cosine theta, and the z is going to equal our sine of theta. So basically what I'm trying to say here is our bounds will be dr d theta now. So procedurally there's nothing different about it. What's our radius? Well, we know that y squared plus z squared, well, once again, since our y is equal to our cosine theta and our z is equal to our sine of theta, if I really just expanded that, this is just going to be r squared cosine squared of theta plus r squared sine squared of theta is equal to 1. And if we factor out that r squared, we're going to have cosine squared of theta plus sine squared of theta is equal to 1. And our favorite identity, we know that's going to equal 1. So our r squared is equal to 1. Therefore, our r is equal to 1. So we know that our bounds on our dr go from 0 to 1. And we know that this is a circle, so therefore it's just going to go from 0 to 2 pi. Y squared plus z squared, well, I just solved for that right here. That's just going to be equal to r squared. So this is actually going to be a pretty simple integral to solve here. R squared, r dx dr d theta. Evaluating this integral now should be pretty easy. We're going to have 3 on the outside multiplied by 0 to 2 pi integral, the integral from 0 to 1. And then we're going to have r cubed, the integral of r cubed dx is going to be r cubed x, and then that x is going to be evaluated from 0 to 3. Dr d theta. So we're actually going to have another 3 there. We can just go ahead and pull that out. We're going to have 9 on the outside from 0 to 2 pi, from 0 to 1 of r cubed dr d theta, which is going to equal 9 times the integral from 0 to 2 pi. And then integrating r cubed to dr, that's going to be 1/4 r to the 4th from r is equal to 0 and to r is equal to 1 d theta. Plugging in 1 there, we're going to have 1/4 times 1 to the 4th, which is going to be 1/4. And then we're subtracting 1/4 times 0. That's just going to be 0. So this is going to be 9 times 0 to 2 pi of 1/4 d theta, which is going to equal 9 times 1/4 theta, evaluated from theta is equal to 0 to 2 pi, which is going to equal, finally, 9 times 2 pi over 4, which is going to equal 9 pi over 2. Not really too many notes on this one that I haven't already reiterated. Once again, just really want to hammer this into our minds that the divergence theorem works when our surface is closed, meaning instead of having just kind of like a little pipe going on here, because we're bounded by those planes x is equal to 0 and x is equal to 3, that means we are closed. If it weren't like that and our x went from 0 to 3, that means it would be a pipe, where now we kind of have like a soup can. So that's kind of the biggest thing I have to say about this problem here. One more note is that we can use cylindrical kind of conversions no matter how we want it, right? So if this was opened up in the y direction, so if we had x squared plus z squared is equal to 1, it doesn't matter. We're still going to be able to use cylindrical conversions, wherein our horizontal is equal to our cosine and our vertical axis is going to equal our sine of theta. So don't let that kind of stray you from doing the right thing and stray you from, I know how to do this. So I guess that's my final note on divergence theorem, and that is also my final note for Calculus 3. Thank you very much for watching.